The stress strain curve actually describes the behaviors of a material. If a material, you stretch it, you create a certain so-called strain. Alright, or this is actually a changes in the length, or a small change of the length itself. Alright, and when you release the forces, this thing over here may actually go back to its original length. Alright, and this going back to the original length, alright, after you stretch it, is considered the elastic region. Alright, when you talk about the Hooke's law, alright, this thing. And this equation describes is a constitutive equation talking about the behavior of elastic region over here. Alright, which is a linear elastic region, you have to say. Alright. So for example, if you apply a certain forces, 200 Newton. Alright, we are also over 200 Newtons over here. Okay. This stresses talks about the stresses over here. Alright, this particular stress, 200. Okay, so far so good. So this is the elastic region we're talking about. And this 200 stresses increase somewhat your distance of a change, and this distance of the change divided by L is equals to your strain, and therefore this strain is reflected directly over here. Alright, at this region over here, because this is a strain curve. Alright, so this is somewhat your 200 force Newton strain. Alright, if you were to apply. Now if you were to apply a 250 Newton now, right, which is somewhere at the yield strength of this particular point over here. Alright, 250 Newton. This is the stress. If you take a look, this is the stress axis. So if I were to apply a 250 Newton, alright, actually further increase the change of length. Alright, so the change of length divided by original length will give you another strain. Alright, this strain will be an increase of strain, and therefore talking about this particular point over here. This is for your 250 Newton. Alright. Now, in order to go all the way up to here, you're gonna apply more stress, right? As you can see from the curve itself. Alright, so when at this particular point over here, this yielding, alright, you may require somewhat 250, maybe up to 270 Newton. Alright, up to here maybe it's 270 Newton. So it's somewhat about the same. But when you start to go into the strain hardening part, you require a more stresses, maybe 350 Newton. Alright, because this is somewhat the natural phenomenon of a material itself. So once you stretch it up to a certain strain, or up to a certain length, maybe you may actually extend up to here. Alright, you may require a higher amount of stress to further increase its stress, to further increase its changes of strain. I mean its changes of so-called length, I would say. You talk about it in this manner. You have require more stresses over here, and the more you go, the more it is of a stress that you requires, and up to a certain point, you actually collapse, become softer and fracture. Alright, it may feel a bit boring, but now let's do an example. I mean, in terms of certain concepts. Therefore, to describe the plastic behavior that is talking about this thing over here, or most probably we're going to talk about this thing over here, which is dealing with these things that we have said earlier. When you're talking about plastic behaviors, the best thing you're going to do is to talk about plastic bag. Alright, so plastic bag, normally when you just first buy it, is a pre-manufactured item, which is a very nice shape. Alright, and therefore it's somewhat similar to your original shape over here. Alright, and when you apply a certain little stress, it may actually extend a little bit and maybe go back to its original state. Alright, but when you start to put items inside, maybe your KFC, your Coca-Cola, everything, alright, you may exceed your yield strength, which is over here. Alright, and maybe continue to extend its length. Alright, so normally when you operate a certain plastic region, alright, at the yielding part, the strain may increase quite significantly, and this is also reflected in this portion over here. This first picture, if I were to show you, I mean this one, okay. So this is somewhat in the yielding portion. alright, certain significant amount of forces larger than the yield strength of the plastic bag, alright, you can still tahan. Alright, so far so good. Then when you reach this point over here, this particular point, you may have increased a significant amount of strain, right? Because this is strain talking about the changes of the length divided by the length. So if the strain increases, this means that your changes of the length actually increase, meaning this changes. Alright, it's gonna increase quite significantly. Alright, so therefore reflects this region over here. You kind of stretch it more, but it's still kind of safe. Alright, and over here, if you were to put two more things, maybe I put another KFC or McDonald's. I put a lot of stuff inside now. Okay, if you were to put two more stuff inside, you're gonna further increase this. Alright, but however, if you were to keep using instead of putting more stuff, you were to keep using this plastic bag all along and putting in the same amount of stuff, alright, it should be safe. You should be always within this region over here. Alright, this region over here. You should be always within this region. Unless you put more stuff inside, you're gonna subject your plastic bag to more of a strain. Alright, more stretch. You're gonna stretch your plastic bag more. Alright, and this is talking about strain hardening, because strain hardening, every time you put in more stuff, alright, you're gonna cause more strain. Alright, so when you put maybe another stuff, two more stuff over here, right? So this thing will stretch. And you can keep using this amount of weight. Maybe this is 5 kg now. You can keep using 5 kg, and it will always be at this particular point. Maybe at this particular point over here. Alright, it should be safe all along, and the strain is always that strain. Alright, and therefore, if you were to increase more, if you were to put more stuff, alright, put more stuff, maybe like Matiam, and now it's 10 kg. Okay, you're gonna somehow reach its ultimate stress over here. And if you were to further put more stuff, the plastic bag itself cannot hold anymore, and it will fracture and eventually go to fracture. Alright, so the strain hardening part, as you can see, you can somewhat understood what is coming on. Alright, therefore in this page over here, you can see that in the plastic region, the true stress increases continuously, which is continuously over this thing over here, as you can see. Alright, and this implies that the metal, alright, in our case it's plastic bag, is becoming stronger as the strain increases, which is as this strain increases all the way to from the strain hardening part over here. Alright, and this is just the strain hardening. And why is it becoming stronger? If you were to go back to our picture over here, you can continue to put more stuff until it reaches your ultimate strength, which is over at this side, alright, which is the maximum 10 kg already. Then you will start to fail. But over here, as you can see, the more stress you put, maybe 8 kg, you'll create more strain. At 6 kg, you create more strain. You get what I mean? So the more weight you put in, the more strain you will cause. But it is still getting more and more stronger. Up to a certain point, it fracture. Alright. For this talks about material. If a material is a metal, or if you want to manufacture it and become a banded stuff, alright, this region here or the whole material itself may actually yield, right? Because you have permanently deformed it. Plasticity is talking about deforming or permanently yield the certain stuff. So we want to know that whether can we bend this metal such that it doesn't cross this ultimate stress and eventually fracture. Because when you bend, maybe halfway when you bend, this whole thing actually crack, and the whole thing pijia, and then become two piece. Then you cannot do anything already ma, right? And otherwise, if you were to successfully do this, then somebody actually sits on it, and then there will be two forces over here and here, right? These two forces. And a long time, if this joint over here isn't strong enough, this whole thing will crack also. So we're actually keen to look at all this stuff that relates to your plasticity and your strain hardening course over here in a more deeper sense. Alright, so this I'm going to talk about two focus in the next few series of our videos. Unlike the elastic region, it talks about the Hooke's law as the constitutive equation. We're going to use another formula which is over here for this region. Alright, and this equation is this. Alright, your strain, okay, is somewhat equivalent to this equation that you're going to use. Alright, so you're gonna talk about these things, but before going into this, as you can see, this equation is really macam already. So what we're gonna do, alright, so the first thing is the equation itself. Before going into the equation, before we go to the equation, we're gonna talk about what is considered safe. Alright, safe using. We need to come out a criteria. Alright, using some concept of this phenomenon of the stress strain curve of different materials. Alright, we're gonna consider what is considered safe, and then we will go to the equation much more easier and readily. The concept of safe comes with this thing. When you put significant load into this system, alright, maybe this is like 1 kg, this is considered safe, right? Because it can still tahan, you can hold it and swing it all around, it should be safe. Alright, when you slightly to go into maybe 3 kg now, right, you start to get a little it's still safe, but slightly to be less unsafe, right? More unsafe, sorry. The more you put in your loads, you're gonna be more and more unsafe. Alright, same as your stress strain curve. The more you go, the more when you apply your more stresses, this is your stress, this axis is your stress, right? So the more you put in your stress, you see your strain is gonna increase, and the strain is gonna increase up to an ultimate stress point. Your whole thing will collapse, which is reflecting this plastic pipe case. If you put in more than 10 kg now, when you have a 10 kg inside, it can barely tahan already, it can barely take it already. And if you were to put more things, then this thing will gonna fracture. Alright, so we're gonna talk about how to actually neatly sort all this safe or unsafe within a certain diagram. Alright, and then we can somewhat go into talking about the equation itself that deals with the phenomenon within it, because this equation itself is somewhat yeah, it's something of a changing of the properties of a material, or with regards to looking at the strain itself, the changes of the L. Alright, maybe this delta L, if you were to talk about it, we are keen to know how long is this delta L and things like that, which is a little more deeper sense. But that's why we say that we're gonna go into the safe criteria first before we talk about the equation, and then we will do some examples and see how these two are linked so succinctly and things like that. And we'll start off with the safety criteria in the next few videos, because yeah, so yeah.